I'd like to look at the beginning of Chapter 9, Testing a Claim, and the introduction to significance tests, the basics that we'll go through with doing a significant test. After this section, we're going to learn how to state null and alternative hypotheses. We'll talk about a p-value, what a p-value is, how to interpret it, to determine whether results are statistically significant, and figure out how to use that p-value to make a good conclusion. And we'll discuss type 1 and type 2 errors and be able to discuss those and interpret them in context. So all of that's probably a little bit confusing to you at this time. Let's look at this. Confidence intervals are one way of looking at data. Another method used in statistical inference is called a significance test. In a confidence interval, I'm trying to estimate the parameter. I'm going to end up pretty sure, fairly confident, 95% confident perhaps, that the true parameter is in the interval that I create, or in the confidence interval that I create. Back that up one. With a significance test, I'm trying to assess the evidence that I get from the data to measure its value or to see how strong that evidence is. The significance test starts by finding some data and comparing that against an original claim called a hypothesis. The results will tell me how likely it is that I could get such an answer given the original hypothesis. So for example, consider a basketball player who claims to make 80% of his free throws. Now, I don't really know if he's telling the truth or if he might be exaggerating, so I'm going to have him shoot some free throws and see how he does. There's an applet that does this that I won't take us through, but he takes some free throws, and at some point, I either decide, yeah, he probably is an 80% free throw shooter, or I think, he shot a bunch of free throws, and I think he might have been overstating his claim. A hypothesis test, or a test of significance, helps evaluate his claim based on the data that we see. A significance test starts with a careful statement of the claims we want to compare. The null hypothesis, written H sub 0, is called the hypothesis of no change or no difference. This is the original starting point. The alternative hypothesis is what we're trying to find evidence for, and this is called HA. In our free throw shooting example, the null hypothesis is that the proportion of free throws he makes is 80%. The alternative hypothesis is that his free throw shooting percentage is actually less than 80%. And they've defined P as the long run proportion of made free throws. Not how many free throws he'll make in the next 25, but over a very long time period, how many free throws we can expect this shooter to make. In a significance test, the null hypothesis is always written HO parameter equals something. So this could be mu or sigma or p or some parameter. And the alternative hypothesis is the same parameter is either less than, greater than, or not equal to this original value. So in our example, the null hypothesis was the parameter equals 80%. The null hypothesis could have been less than or greater than or not equal to. In this case, we chose less than because we think that in the real world, this free throw shooter might not shoot as well as he claims to shoot. To determine the correct form for the alternative hypothesis, read the question. An alternative hypothesis is one-sided if it states that it's either less than or greater than. A two-sided alternative hypothesis is this not equals 2 case. And this will make more sense as we draw pictures of these in a moment. The null hypothesis should express the hopes or suspicions we have before we see the data. It's the hypothesis of no change or no difference. I don't look at the data first and then write my null hypothesis or my alternative hypothesis. I start out with my hypotheses, the HO and the HA, and then I go and look at the data and see what they tell me. Hypotheses always refer to the population. They're written in terms of parameters because they deal with populations, not with samples. It's never correct to write a hypothesis about a p-hat or an x-bar. Instead, we'll write it about p or mu. Suppose a basketball player claims to be an 80% free throw shooter. To test the claim, we have him shoot 53 free throws. He made just 32 of them. In our sample, he's made 64% of his free throws. 80 seems to be a bit high, but could an 80% free throw shooter make only 64% when he shoots 50? We could do a simulation and maybe have 400 minions shoot 50 free throws and see how many they make. In this case, here's the graph that I get when I graph my 400 minions simulation. How many of these simulations are around 64%? Here's 64%. Only 3 out of those 400 times did I get an answer way down here. Now, this is assuming that he really is an 80% free throw shooter. If he's an 80% free throw shooter, it's pretty unlikely that he'd only make 64% of his 50 free throws. We can measure how strong the evidence against a player's claim is by giving the probability that he would make as few as 32 out of 50 free throws if he really makes 80%, if he's really an 80% free throw shooter. Based on this simulation, it's pretty unlikely. It, in fact, only happens 0.0075 or 0.75% of the time. This is so small, it's really unlikely that this guy actually shoots 80%. There's 2 reasons why he could have come up with an answer like 64%. One reason is he just had a really bad day. He really is an 80% free throw shooter, and just by pure luck, or in this case, unluck, he didn't have a very good free throw shooting day. Or, on the other hand, maybe HO isn't true, and in fact the alternative hypothesis is right, that the truth is something less than 80%. The basic idea is this: an outcome that would rarely happen if the null hypothesis is true is good evidence that maybe the null hypothesis isn't true. In other words, for this problem, if he shoots 80%, it's really unlikely that we would catch him on a day that he only makes 64%. So maybe he's not really an 80% free throw shooter. The null hypothesis, HO, states the claim that we are seeking evidence against. The probability that measures the strength of the evidence against that null hypothesis is called the p-value. So for the problem that we just examined, the p-value is 0.0075. The probability, computed by assuming HO is true, that a statistic would take a value as extreme or more extreme than the one we actually got is called the p-value of the test. Small p-values are evidence against HO because they say the observed result is pretty unlikely to occur if HO is true. On the other hand, a large p-value will fail to give convincing evidence against HO because they say the result we observed is likely to have occurred by chance if HO is true. The final step in performing a significance test is to draw a conclusion about the competing claims you are testing. We make one of two decisions based on the strength of the evidence against the null hypothesis and in favor of the alternative hypothesis. We'll either reject HO or we'll fail to reject HO. Note, when I fail to reject HO in a significance test, that doesn't actually mean HO is true. For that reason, you should never accept HO or use language implying you believe that HO is true. In a nutshell, our conclusion in a significance test comes down to this. If I have a small p-value, I'll reject HO because I have convincing evidence to believe HA. On the other hand, if my p-value is large, I will fail to reject HO, and I do not have convincing evidence to believe HA. There's no real rule for how small a p-value should be to require us to reject HO, but we can compare the p-value with a fixed value that we regard as decisive, and that's called the significance level. We write it as alpha. I don't know why it's printed as a little box there, but the Greek letter alpha kind of looks like a fish, is given for the significance level. If the p-value is smaller than alpha, we say that the data are statistically significant at level alpha. In that case, we reject the null hypothesis HO and conclude that there is convincing evidence in favor of the alternative hypothesis, HA. When we used a fixed level of significance to draw a conclusion for a significance test, if the p-value is less than alpha, reject HO. If the p-value is greater than or equal to alpha, I will fail to reject HO. Type 1 and Type 2 errors. When we draw a conclusion from a significance test, we hope that we're right, but sometimes our conclusion is wrong. There's two types of mistakes we can make. If we reject HO when HO is true, we've committed what's called a Type 1 error. If we have failed to reject HO when HA is true, we've committed a Type 2 error. And this table gives us an idea of how this looks. If HO is true, but I reject it, it's a Type 1 error. If HO is true, and I fail to reject it, I've made the right decision. On the other hand, if HO is false, and I reject it, that's a correct decision. But when HO is false, and I failed to recognize that, so I failed to reject it, I've made what's called a Type 2 error. The probability of a Type 1 error is the probability of rejecting HO when it's really true. This is the significance level of the test. So the significance level alpha of any fixed level test is the probability of making a Type 1 error. That is, alpha is the probability that the test will reject HO when HO is actually true. And we want to consider the consequences of making that error when we decide what alpha is. When we put this in a context, that part will make more sense to you. This section has been a quick overview of the null and alternative hypotheses. We discussed interpreting p-values and determining whether results are statistically significant and how to use that to make an appropriate conclusion. Finally, I briefly introduced Type 1 and Type 2 errors and told you what those things are in this context. It's a brief introduction to section 1 in chapter 9.